let's do a quick review of lecture 3. So last time we talked about two key ideas about GPS, right? One was how does the receiver determine the position of the satellites? And we said that's done using the information in the navigation messages, specifically the ephemeris part of the navigation message has 6 parameters in it, which are called the orbital parameters. And with these parameters, 3 of them determine basically an elliptical trajectory of the satellite at a point in time, and also the position of the satellite within that ellipse. And the other 3 determine the orientation of this elliptical plane with respect to the Earth-centered, Earth-fixed coordinate system. Okay, so with those 6 parameters, the receiver can estimate very accurately the position of the satellite at a given point in time. There's also some correction parameters that tells the receiver how each of these 6 parameters change over time, so the receiver can extrapolate or interpolate between 2 navigation messages and continuously track the satellite's position very accurately. So that was the first thing. The second key idea we talked about, we kind of demystified this idea of time of flight estimation using ranging codes, right? So we basically derived the least mean square error estimate of the time of flight in a very general setup, right? We formulated it as an optimization problem. Some signal x of k is transmitted, which its waveform is known to the receiver. The receiver measures y of k, which is an attenuated and delayed version of x of k. And then we showed that the optimal estimate of n sub tau is given by the index at which this correlation function is maximized, right? So you calculate this thing, which is very closely related to a convolution. And if you calculate this function, kind of you can also think of it as a linear filter with kind of like the kernel or the impulse response of the filter being x of minus k or something like that. And then you can calculate this function. And if you plot its absolute value, and the absolute value is because sometimes there could be sign flips, so that's why you take the absolute value, or you can also square it. And you find the peak, and the index at which the peak happens is your best estimate of the time of flight delay in the least square sense. Okay? And then from this, and this is true about any signal, right? Whatever x you send, if this measurement model is valid, as long as this is a valid measurement model, then the correlation is basically the optimal way of determining your time of flight. But what is interesting about this is then for when you're designing a system, you're free to choose what x of k is. And then based on this, because at the end of the day, it's a correlation function that matters, you can choose an x with good correlation properties. And by good properties, we mean a nice sharp peak, so you don't want this peak to be too broad, for instance, because then finding the peak, the actual maximum point of it could be a little tricky in noisy situations. And also, you want the side lobes to be very low. Okay? And then it turns out that there's many different codes, as we call them, that have good properties. The specific class that GPS uses are called M sequences, also called maximal length sequences. And we said that these are good because they have specifically 3 very interesting properties. They, of course, have good correlations, as we showed. They have these triangle functions with constant, very low side lobes. They're extremely easy to generate. All you need is basically a shift register with n bits and some feedback taps, and then you get a code with a number of chips that is equal to 2 to the n minus 1. So with just 10-bit shift register, you can generate a code that is 1023 bits or chips. And also, you can generate multiple codes of the same length with different shift register feedback taps. And those codes, each of them has very good autocorrelation, and the autocorrelation functions are, in fact, exact same between those, but the cross correlations are very low. And this low cross correlation is the key idea behind code division multiple access, because the receiver can essentially have different correlators with different kernels, and each of them only responds to the specific code that is the kernel of that correlator. And if you pass a different code through it, you basically get not exactly 0, but very low output. Okay? Any questions about this? Yes?
Question about, you said that you should take absolute value in case there are sign shifts. Like, what's an example of like a sign shift?
So an example of a sign shift is, for instance, well, here we said alpha is just an attenuation factor, right? In reality, alpha can be a complex number because there's also phase effects, right? And once you make your alpha a complex number, if you have a 90-degree phase shift, that's like a minus sign, right? So this alpha, if the phase effect gives you like a 90-degree phase shift, can flip the sign of your x, for instance. That's one example. So generally, yeah, that's why we take the absolute value or squared. Okay, any other questions? All right, so let's continue the discussion. So we said this was sort of like the ideal case, but we said there's like 3 complications or non-idealities that the receiver has to deal with. First one was the Doppler shift, right? And we'll get back to it and show you like how Doppler shift is compensated for. The other one was the fact that the receiver clock is never perfectly synchronized with the GPS clock, right? So what happens is that there's some extra shift in here just due to the receiver clock offset that also needs to be compensated for, and that's what we call tau sub d. And because of that, the receiver doesn't recover the physical range. It recovers what we call the pseudo range, right? And the third one, which we didn't quite finish, we just set up the problem, is this idea of range ambiguity. And the idea of range ambiguity is, so the signals that are being transmitted are periodic. So the correlations also are periodic, right? We usually just calculate it over one period of the signal, right? So in here, for instance, if this was in this picture, if this was a CA code, your correlation, you can start from index 0 and only go to 1022, right? Only one period of your signal. But in reality, the n hat that you find from here, the physical n hat, can be that plus any multiple of the code length, right? So it could be n hat 1 plus k, plus 2k, plus 3k, and so on and so forth. And that's why we have this ambiguity in our ranging, and we need to exactly find what is the correct, so the actual physical time of flight is n hat 1 plus some m times k, and remember k is the number of samples in the code, and we need to find what is m. Is m equal to 1? Is it 2? M is an integer, right? So you need to disambiguate that integer m, which corresponds to the physical range. So how can we do this? There's a simple solution, which is basically if we have some idea, roughly, of what the actual time of flight delay is, or what the actual pseudo range we expect from the satellite is, okay? Roughly, doesn't need to be exact. But if we know that, so that can help us disambiguate between these solutions, basically, that we get from the correlation. So for instance, one thing we know is that the GPS satellites, they are orbiting the Earth at an elevation that is 2,200 kilometers, okay? So if the receiver was exactly below one of these satellites, then the range would be 2,200 kilometers. But in reality, these satellites cover a large portion of the Earth, so your range or pseudo range can be hundreds or possibly thousands of kilometers away from this number, okay? That's still okay. That's a ballpark number to work with. So let's see if that is useful for disambiguation. So in order to see what we can do, we need to know basically what is, from one peak to the next, what is the delta range, right? And is that large or small compared to this number? If it's very large, then only one of the peaks would be very close to this number. So let's calculate that. So the range variation, delta R, is C times the delta tau. And the delta tau we are talking about is between two, basically, adjacent peaks in this extended correlation function. So what is the delta tau? It's basically the number of samples between two of those peaks times your sampling time. Number of samples, it's basically m times n. So remember, this is our k, right? Total number of samples in a discretized code, and this would be equal to n times the chip time interval, or also you can write it as c times the total duration of the code, right? So that's the delta range that you get between two consecutive peaks. So what is that actually equal to? Let's look at a few numbers here. So for instance, if you're working with the PY code, this was the military code, let's see what the range ambiguity for that is. A chip duration for that is 97.8 nanoseconds, and it has very large number of chips. Remember, this was 6 times 10 to the 12 chips. So you calculate your delta R, it comes out as 1.8 times 10 to the 11 kilometers, right? With this delta R, it's very, very easy to disambiguate, right? Because if your peaks are in the extended correlation are this far apart, of course, there's only one of them that is even remotely close to this number. So with PY, not a problem, right? You can easily disambiguate your range. How about the civilian code? Let's look at the CA code. So the CA code, remember, was much, much shorter, right? So it has a chip duration of 977.5 nanoseconds. Total number of chips is 1023. Plug the numbers into our delta R equation, it comes out to almost 300 kilometers. With this, we have a problem, right? Because if these peaks in the extended correlation, I'm going to go back, if these peaks are only in range 300 kilometers apart, we cannot decide which one. We can be, multiple of them could be the actual physical range, right? It's not enough separation to let us disambiguate. Yes?
It's the one that has like the lowest correlation, so for like a lowest distance.
Well, because that the question is why not pick the peak, which is, do you mean closest to the 20,000 number? Is that? Okay. Because physically that might not be right. So if I draw a picture here for you, let's say this is the Earth, and we have a satellite here. Okay. Remember, these satellites cover a very large surface area, right? Very wide beams. So if your receiver is directly under this guy, if you're here, then you're 20,000 K. Okay? But if you're here, you could be 40,000 kilometers or something. I mean, we can't exactly calculate. I don't know off the top of my head like what's the delta is. But this can be, yeah, thousands of kilometers away from 20. And if our delta ranges are only 300 kilometers, it is not enough. Okay? So the simple idea doesn't work for the civilian code. What do we do? It turns out that this range disambiguation, there's multiple ways around it, and different GPS manufacturers, they kind of have their own secret sauce of like how they do this, and they don't, of course, tell us what they do. But there's ideas out there and which can work. So if you were to, for instance, implement your own, you can pick some of these. And there's more than the 3 ideas listed here, but these are the easier ones. So one is, well, the range from, or the pseudo-range from each satellite is ambiguous, right? But we always have multiple satellites to work with. So you can use your multiple measurements, and remember, these should define spheres that intersect at almost one point. So based on that geometric constraint, that can help you disambiguate and pick the pseudo ranges that are geometrically consistent. Okay, so that's one idea. The other one is, even with just one satellite, if you wait for the satellite to move a little bit in orbit by a non-negligible amount, then that movement, you know the exact trajectory of the satellite. And again, that's another geometric constraint that can help you disambiguate what's the true range. You can pick the pseudo range that is consistent with your trajectory of the satellite that you're estimating. So that's the second idea. The third one doesn't have any basically geometry grounding. It's more about the structure of the bits in the LNAV messages. So there's this thing called the bit synchronization, and that has to do with how the codes and the navigation message frames are arranged inside the GPS data packets, and that bit synchronization can help you disambiguate. It gets a bit technical, but I just wanted to put the idea out there in case you want to read more about it. So those are some ideas, and you could use these or other ideas to disambiguate. But an important point is this range ambiguity, it's only a problem to solve when you cold start your receiver. And by cold start, we mean you just turn it on, you have no idea where you are, it's the very first position fix that you want to make, and then you have this ambiguity problem. As soon as your first position fix comes in, for the next one, you can always use your previous estimate to disambiguate, right? Because remember, for instance, the CA code is updating every millisecond, right? So in principle, every millisecond, you can update your position, and in a millisecond, you're not going to move by much, or your pseudo range is not going to change by much. So you can always look at the previous one and then go back to the simple idea and say, okay, my previous pseudo range was 25,000 kilometers. My next one, I just choose the peak that is close to that, okay? So this is, again, it's only a challenge after a cold start. You do your first thing, and then you get going with the simple method of range disambiguation. Okay, so with this, I think we have cleared the two important things that the receiver needs to do. We now know how the locations in orbit are calculated for the satellites, and we also know how time of flight is calculated using the ranging codes. The one thing we have not clarified yet is or two things. One is how is Doppler shift estimated, and how is the timing offset compensated for, okay? So we'll talk about those. And of course, we have not yet gotten to a point where we actually use these pseudo-range measurements to localize ourselves. That's also a topic of the discussion for today. Any questions before we continue? Okay, so we talked a lot about the physics. We developed a signal model. We also developed a mathematical model of how ranging using these codes work. Now we are at a level where we can start looking at the GPS receiver from a system level, right? So now we're going to build a system model for the GPS receiver. Let's look at the transmitter very briefly. We're not going to spend too much time on it. So this is the satellite model. In reality, it's a lot more complex than this, but what we care about is that there's a local oscillator that generates a carrier frequency, and then there are two signals modulated on it, right? So there is the X of t, which is our ranging code, let's say the CA code, and then there's a DET, which is the navigation message, and the data rates are very different. One is very fast, megabits per second. The other one is very slow, bits per second, and then basically the signal is transmitted to us via an antenna. Right? And this is the signal model. And here, just to make the math a little more tractable, we're ignoring the quadrature. So we assume for now we are only transmitting an in-phase component, right? So that's why there's just the cosine 2 pi FCT. We are ignoring the sine, right? Just to make the math a little easier to track. But everything we say is general. Even if you have both quadratures in there, everything will work out. Okay? So that's the transmitter part. We're going to spend a lot more time on the receiver system architecture. So this is what it looks like. So this is kind of like a system block diagram of what a GPS receiver is. It, of course, has an antenna. It's going to receive a signal called that SR of t. And then from a a high-level functional point of view, these are the main blocks in the receiver. There's an RF front end, and then the signal from there goes to an analog to digital conversion block, or an ADC. Then there is a demodulation block, which takes input from a numerically controlled oscillator, or an NCO. And then the output from that goes to the correlator, which has an input from a local code replica generator. And at the output of the correlation, we need to basically find and track the peak index, which basically is a measure of the pseudo range, right? The demodulation block specifically, what it does is that it finds and tracks and cancels the Doppler shift for us, as we will see. And the correlation block, as we know, basically finds and tracks tau plus tau d, so the pseudo range. Okay, so this is high level. Now, what we are going to do is we are going to kind of double-click on each box, if you will, and go a level deeper and track the signal from the input to the antenna all the way to the output of the correlator, and basically do the full derivation of what happens to our signal as it's processed through the system. Okay, so first let's look at the RF front end. So this here, basically everything you see here is basically inside the RF front end, right? So we're zooming in and seeing what's happening inside what we call the RF front end. Okay, so there's a signal coming in, that's SR. That's the power in it, route to PR, and then there's the navigation and the code signal that are delayed by the time of flight, right? So d of t minus tau, x of t minus tau, and then you have your carrier that is shifted by the Doppler shift, so you get 2 pi of fc, which is the nominal carrier frequency, plus the Doppler shift, right? And there's some phase shift due to basically, again, the propagation delays. And just to make our model more complete, we're adding a noise term here. So this NFT is the noise term, okay? And then it can be any noise model. Usually, white Gaussian noise is what's assumed for these systems, but it can be anything. So what happens here is basically, first you have a low noise amplifier, LNA, and we assume it has some gain G. And then the signal goes through a RF bandpass filter centered at the nominal carrier frequency, f sub c. Why do we have the filter? Because we only want to work with where the information is. Everything that is far away from the carrier frequency is just noise and interference that we want to filter out as early as possible. Then we have our first demodulation step. So what happens here is we have a local oscillator that is generating this sine wave at the nominal carrier frequency, offset at what is called the intermediate frequency. So it's generating a cosine 2 pi fc minus fis t, right? Why that? Why not just demodulate by fc? Why are we going to this intermediate frequency? It's an architecture decision. There's nothing wrong with going basically demodulating right down to fc. But this idea, which is called the heterodyne architecture, it's used a lot in communications. And the reason is, usually if you look at the noise spectrum, the closer you get to DC, things get more noisy, right? There's the 1 over f noise. There's other effects that make basically the DC portion of the spectrum pretty noisy. So you want to delay bringing your signal down to that part of the spectrum to the digital domain, because then you don't mix in all these analog low frequency noises to your signal. So you first bring it, just if I were to draw a picture of the spectrum, so if this is f, what you receive first is centered at fc, which is your carrier frequency. Well, technically fc plus the Doppler shift, but Doppler shift is a small relative to your carrier frequency. This is kilohertz, carrier is gigahertz, right? But anyway, so you have some signal around this. And the first step brings this down, and let's say this is 0, brings us down to some intermediate frequency. Still, we have the FD offset, right? So you come here, And then later in DSP, you bring it further down, as we'll see, to baseband, and then you do your correlation. And again, the reason you come here first and not directly to around DC is that there's a lot of noise usually around here. So there's noise. And you don't want to directly bring your signal to the noisiest part of the spectrum. It's just one architecture choice. There are systems that do homodyne, which brings it directly to the DC. OK, so let's see what mathematically what happens to our signal. So what happens is that, well, first, S is multiplied by the gain of the low noise amplifier. So that's, we're just modeling it as a gain block. So we are not going to the detail of like what the actual frequency response of this is. Just assume signal is in band and it's just this G multiplier. And then you filter it, and then the important things happens at this mixer where you basically multiply this local oscillator output with your signal. So you get cosine of FC minus FIF times cosine of FC plus FD, and you get two cross terms, right? One is at the sum frequency, one is at the difference frequency. The sum of the difference of the two frequencies, the F carrier cancels out, and you're left with this frequency, which is your Doppler shift plus the intermediate frequency. And the second term is at the sum, which goes to twice the carrier frequency, right? So you go to 2FC plus F sub D minus FIF, right? Then what you do is you put a bandpass filter centered at the intermediate frequency, and what the bandpass filter does is it filters out this part, this term, which is at 2FC, right? Because again, in this picture, the one that's at 2FC, this goes way out, right? That copy would be here, centered at 2FC. And then when you bandpass filter around here, this guy goes out. So that's what the bandpass filter does for you. And what comes out, we call it the intermediate frequency or SIF signal. Yes?
Why is there a phase shift on your local oscillator?
Great question. So the question is, why is there a phase shift, this theta tilde in the local oscillator? Because it's not, it's not phase locked to the received signal. So that's just a non-ideality in the system. So the received signal is coming with some unknown phase theta, and I'm generating some sine wave. So this also has its own phase because I don't know the phase of the carrier to lock to it. My local oscillator is free running, so its output is going to have some theta tilde.
Can't you just make the theta on the signal be relative to the oscillator?
You can, yes. Maybe that's a better choice. But I want it to be kind of more explicit in like what's phase locked and what's not. So I'm kind of like intentionally adding the two thetas. But you're absolutely right. I mean, mathematically, you can just say theta is relative to my LO and make this 0. Perfectly fine. OK, so let's continue. OK, so this is again, this SIF is what comes out of your low-pass filter. Just this term at the double, the 2FC is filtered out, and you're left with what is d of t sub t minus tau, x of t minus tau times cosine of the Doppler plus the intermediate frequency, plus the delta theta. So in your notation, this is the delta theta. So I'm just calling theta minus theta tilde delta theta, and that's exactly your suggestion. And then your noises is still there. The noise is also going through this entire chain, right? So it gets filtered, it gets amplified and filtered and mixed down and again filtered. So now we are calling it the intermediate frequency noise. Okay? So next is you have the ADC and the Doppler demodulation, right? ADC is easy, so your intermediate frequency signal is coming in. We are just sampling it with some sampling rate fs or sampling interval t sub s. So you get SIF of n, which is SIF of n times ds. And here, what we have is basically we want to separate out the in-phase and quadrature components of our signal, right? And we also want to compensate or cancel out the Doppler shift, right? So we have what we call a numerically controlled oscillator. So it is an oscillator whose output frequency and phase can be controlled by a numerical input, right? So it takes in a kind of like a nominal oscillator or a fixed oscillator input, and then a second input that is kind of like a knob to tune the output frequency and phase of this thing, right? And let's say, for now, the receiver has some estimate somehow, will tell you where this is coming from, the f hat. But if you have some estimate of what the Doppler shift is, you can tune your numerically controlled oscillator to output a sine and a cosine term that is exactly at FIF plus F Doppler, or F hat Doppler. Okay, so F hat Doppler is the receiver's estimate of the Doppler shift. Okay, and FIF, the intermediate frequency, is known, so because the receiver knows where it brought the, or what intermediate frequency it's using. And then you have to do another mixing, basically, of your discretized IF signal. And one is mixing with a cosine term. The other one is mixing with a sine term. And this is just some algebra here. Again, you multiply the two terms, you get, or multiply them, and you get two terms, one at the sum frequency, one at the difference frequency. And if you put a low-pass filter here, it only gives you the difference frequency output. The sum gets filtered out, exactly as it happened with the first mixer. And you're left with this. So again, we have discretized, so now we have d of nts minus tau times x of nts minus tau times the cosine of, this is, again, we're keeping just the difference frequency, which is the actual Doppler shift, minus our estimate of the Doppler shift, right? So you get fd minus f hat d plus some phase term, right? And noise is also just carrying through. Here, again, so we now have two outputs, right? There's an in phase and there's a quadrature. So that's the SI, and the SQ is exact same, except you have a sine instead of a cosine, right? Now here's something interesting. If somehow your estimate of the Doppler shift is perfect, both the frequency and the phase, okay, then what happens if your estimate is perfect is this term is 0, right? The delta theta term is also 0. So you get cosine of 0 for your in phase, which is 1, right? What do we get for the quadrature? Same thing. So the argument of the sine term becomes 0. You get sine of 0, which is 0. So your quadrature term becomes just noise, right? Which exactly makes sense. So if you are correctly estimating and tracking your Doppler shift and that phase term here, your SI signal just becomes some constant times the LNAV message times the coding range plus noise, and your quadrature signal becomes just noise, which makes complete sense because we started with the assumption that we are not transmitting anything in the quadrature, right? So of course, our quadrature output for now is just noise. If you had a Q component, you would get some real output in here. Okay. Again, this is, I'm going really detailed in here because I think it's important to be comfortable with this type of system level analysis, that like you have a system design, you know the blocks, you kind of, break it down and track your signal down the chain and can exactly derive what is happening to the signal as it's going through each of these blocks. Okay, so now we are on to something, right? Because if you look at here, we have gotten rid of all the carrier modulation and the Doppler shift, right? And we have kind of down to what we care for. We want to get to a point where we just have the delayed X, and then we can correlate it with our local replica and find the peak. And we are very, very close to that. In fact, we are exactly there. Why? Because here what we don't like is, well, this is just a constant, G times root P. That's fine. Multiplicative constant, don't care. Noise is always there. You're never going to get completely rid of noise, so fine. It's going to be some noise added to the output of the correlator. It's the LNAV message here that's annoying, right? But is it really annoying? And the answer is no. Why is the answer no? Because remember, this D varies very, very slowly compared to the coding range, coding signal. range encode. And because this varies very, very slowly, you can assume this d is also constant. On the time scales that you care for correlation, like milliseconds, you can assume d is just either a +1 or a -1, which also is related to the question raised earlier that why do we take the absolute value out of the correlator. This is another case where there could be a sign shift. If our d is equal to a -1 versus a +1, that could make a sign shift at the output of the correlator. But we take the absolute value, so that's not important. OK, so then we are essentially done. So all we need to do is now run a correlation on this demodulated and Doppler compensated signal and find a peak. The way the receiver operates is instead of actually generating one fixed replica code and calculating the correlation for all possible values of n and then doing a peak search, instead it does it the other way around. It generates a shifted replica code by what it thinks the time of flight is. So it generates an x of nts plus tau d, this is the time delay, plus tau hat, which is the receiver's estimate of the time of flight. And then it looks at the correlation just at the 0 index, right? And if this tau hat is correct, then the peak would happen at 0. Does this make sense? So instead of basically calculating r x hat y of n as a function of n, and then searching through this function and finding where our n hat tau is. This is one way of doing it. The receiver actually just monitors the output of the correlator at 0 and instead finds r hat of n minus n tau and varies the n tau as a knob to bring this as it's a linear operation, right? So if you shift the input, the peak is going to shift. You can always just monitor the value of the correlation at 0. And if this shift value is equal to n hat, you bring this peak to 0. And if you maximize this value, that means you found the correct n hat. So that's how the receiver actually operates. It generates the shifted version of shifted replica of the code, and kind of varies the shift, varies this tau hat, until the output of the correlator at 0 is maximized. And then it's like, I found the tau hat because I perfectly aligned what I received with the shifted replica of the code, and that's my tau hat. Okay, and mathematically again, this is what it is. I mean, don't get scared off by this. I've put everything in there just so you get comfortable with like this level of detail when you're analyzing your system. But we can break it down. Again, this is just all the multiplicative constants, right? G was the gain of the low noise amplifier. Root PR is the received basically signal power. D is our navigation message. I'm taking it out of the summation because we said we can assume it's a constant, right? So this D is either a +1 or a -1, depending on what the value of the LNAV message was at the time. This 1 over NC is just the constant for the cyclic correlation because it's a normalization constant by the number of samples. And then the summation inside this is what you've received, x of nts minus tau, right? The discretized range encode. This one is what the receiver generates, right? So it's the copy of the code or the local replica of the code, which is nt sub s. Again, it's sampled at the same sampling rate. There's a plus tau d here. That's the timing offset of the receiver. And then this tau hat, again, is what we are trying to find and match it to tau, right? So the receiver varies tau hat and looks at this number, which is the value of the correlation at 0. And when this number SI is maximized, that means your tau hat is equal to tau, because you have perfectly aligned things. Yes?
Tau hat minus tau d be equal to tau for maximum.
Oh yeah, you're exactly right, and it's actually tau hat minus tau d. I was assuming tau d is 0, but you're absolutely right. Again, what is this cosine? We'll get to that, but let me finish this. So what is this cosine term here? That's basically the residual modulation if your estimate of the Doppler shift is not perfect, right? So this delta f here is the actual Doppler shift minus your estimate of the Doppler shift. If you are estimating Doppler shift perfectly, this becomes 0, the delta theta becomes 0, and this whole cosine term becomes 1. It doesn't matter, right? But it's very important because this means if you are not estimating your Doppler shift correctly, you get this extra cosine term inside the summation, and that can completely kill the output of your correlator, as we'll see. So that's why it's essential to have Doppler compensation. If you don't, it can significantly reduce that peak value or even entirely kill it. So just to summarize, again, we are assuming d of t is equal to either plus or minus 1. So we assume it constant in the time scales of the correlation. And to maximize this, what we call S sub I output, two things need to happen for that thing to get maximized. One is, as I said, you have to track and compensate for Doppler correctly, so that delta f term should be 0, which means your estimate of the Doppler shift should be equal to the actual Doppler shift, and also your estimate of the phase should be the actual phase, and that makes that cosine term 0. That's number one. Number two, which is exactly what Saksham said, is your tau hat should be equal to tau plus tau d. And the tau hat, again, is like, as you generate this local replica of the code, you're shifting it around by tau hat and seeing at what value of it I'm maximizing my correlator output. And the value at which it maximizes is exactly tau plus tau d. If tau d was 0, if you had no timing offset, that means you had found the actual physical time of flight. But because it's always non-zero, you find the time of flight plus your timing delay. Okay? And this is graphically what it happens. Again, assume we're plotting things as a function of the tau hat, which is how much the receiver shifts around the replica code that it's generating. And this is the output of the correlator plotted as a function of tau hat. So it's a small, 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 and suddenly it peaks. And it peaks where your tau hat is equal to tau plus tau d. And once you find that peak, you just hold it there. You're like, I found the peak, and that's my time of flight, all right? Or time of flight plus my timing offset. So this is for the in phase. The quadrature output is just noise. So you just feed noise to the correlator. You get noise out. There's no peak. And that makes sense because we didn't send anything over the quadrature in this example. If you had another code over quadrature, that correlator would also have its own peak, related to the other ranging code. Any questions? Does everything really make sense? Because I assume some stuff should not fully make sense. So feel free to ask questions. I mean, it's important to clarify things. Still no questions? All right. OK, so this was kind of like at a system level. Again, let's look at this slide real quick. So we fully basically traced signal from the input of our receiver system through the entire signal chain, from the amplification, the heterodyne down conversion, analog to digital conversion, and then the second step demodulation with the Doppler tracking, and then finally the correlation, and then tracking finding this peak at the correlator output, which happens when two things are correct. One is our estimate of Doppler should be correct, and our estimate of basically the time of flight plus our timing offset should be correct. And that's when we get a large peak at the output of the correlator. Okay. Now I still haven't told you how do we make these two conditions satisfied, right? So you still need to, again, you cold start your receiver, how do you estimate Doppler? And how do you make f hat equal to f hat d equal to fd? And how do you set your tau hat equal to tau d? It's actually pretty straightforward. So that's this idea of acquisition and tracking. So after a cold start, there's two phases of operation for a GPS receiver. The first one is called acquisition. And in the acquisition phase, basically, the receiver needs to find its first estimate of what the Doppler shift is and what the pseudo range is, or the time equivalent of it, which is tau plus tau d. For multiple satellites, right? For at least 4 satellites, you need to find both the Doppler shift and the pseudo range, or the time equivalent of it. And after that, that's called the acquisition phase, right? Which is typically slow. It can take 10 seconds, for instance, for an older GPS receiver. And after you find that first estimate for every satellite of fd and tau plus tau d, then you can go to a tracking phase, because from there on, the first estimate is a little trickier to find, but afterwards, because you're operating on very small time scales, you can just track. These things are going to vary slowly. Like, you always have a previous estimate of your Doppler shift, and for your next estimate, you use your previous estimate as a starting point, and you just track the variations of it around your previous estimate. Same for pseudo range. You always have your previous one, and the next one you can just track how much it changed. So tracking is fast because you have a very good estimate already of where these values should be. Okay, so let's start with the acquisition. Essentially what you have to do, you have a 2D search space, right? One dimension is Doppler shift. The other dimension is tau hat, or the time equivalent of the pseudo range, right? And what's good is that both of these are bounded, right? We said, for instance, that Doppler shift for typical applications of vehicles and robots on the surface of the Earth is bound to plus or minus 10 kilohertz, all right? And then for your tau hat, because these correlations are periodic, you just need to search over one period of the correlation, which, for instance, for a CA code, you have 10,023 chips to search through. And that's exactly what the receiver does. So again, for a coarse acquisition code, you have f hat between minus 10 and 10 kilohertz. You have tau hat between 0 and 1 millisecond. So 1 millisecond, again, is the duration of one full ranging code. And you perform a 2D search. Here's the graphically how it's done. So you have two axes. You have your Doppler shift going from minus 10 to 10, and you have your tau hat. I'm showing it in units of chips, but you can also convert that to time. So it goes from 0 to 1023, or in time, it goes from 0 to 1 millisecond, right? And then you do a grid search, basically. That's exactly what the receiver does. So you start from whatever combination, like Doppler shift minus 10 kilohertz and tau hat 0, and you monitor the output of your correlator. That's just one number, right? That SI that was coming out of your correlator. And you do your grid search. You just, search the grid in some pattern. And when you hit the right combination of Doppler shift and tau hat, you get a very large output out of your correlator. And you typically have some acquisition threshold, and you monitor the output of your correlator, and when it goes above that, you're like, all right, I acquired my satellite, which means I have an estimate, a very good estimate of both the Doppler shift and the pseudo range, right? You can look at slices here just so you get an idea of how sensitive you are to residual errors in tau or in Doppler. Usually, the way these codes behave mathematically is that in tau, you're extremely sensitive. So here's a slice for I'm showing a slice of this 2D function for the correct Doppler. So here already we have found the correct FD, and we are just varying tau here, right? And you only see a very sharp peak where your tau hat is equal to tau plus tau d. And if you're one bin off, essentially, or one chip off in code, you get almost nothing. And that's, again, because that was the mathematical property of these M sequences. The correlation has a very sharp peak, and then it quickly drops to almost 0, right? So that's that. In Doppler, it's a little more forgiving. So if you look at the slice, at the right tau hat, so you have found your pseudo range correctly, and you just have some residual error in Doppler, that's a behavior. It's almost like a sinc function, right? So at the correct Doppler, when f hat is equal to the actual Doppler, of course, that's its maximum, and then it drops. It's still a pretty sharp drop, right? So remember that like end to end, this is just 20 kilohertz, right? But you can be off by a few hundreds of hertz and still have a decent, output out of your correlator. But if you're off by more than, I don't know, like 250 kilohertz or so, 250 hertz or so, you almost entirely kill the correlation output. And that's actually a good thing. This is not a bad thing, because the fact that both these peaks are reasonably sharp, it means that you can very accurately find both the Doppler shift and the tau hat with the 2D search. So this is the acquisition phase, and this is why it's slow, because you need to do a full 2D search over a grid. And I'll get to your question in a second, but real quick, just so you get an idea of how big of a search you need to do. So for a CA code, you want to search all of your range, basically, bins. And so let's say the full code is 1 millisecond, and one chip is 0.98 microseconds. So again, you almost have, or you exactly have 1,023 range bins to search, or tau hat bins to search. And then for Doppler, a typical number for the size of these Doppler cells for the search is 250 hertz. And then you have a 20 kilohertz, basically, Doppler bandwidth to search. So that's 80 times roughly 1,000. So about 80,000 combinations of tau hat and FD that you need to search. And that's why on older receivers, it takes a few seconds. I mean, really, on modern things, this can be done in super quickly. I mean, we're talking probably tens of milliseconds to get the first fix. It's not really that bad, because each of these, remember, to each search, at the end of the day, what you want to get one number out, which is just an inner product with the shifted replica of the code and what you received, and you just want the correlation value at 0, so that's just one inner product that you do, and that gives the value of this function. Question?
Yeah, I hear searching for the peak correlation. Are the Doppler effects going to change?
Yeah, that's why you need to do it relatively fast. Yes. And again, so for instance, if you are on, just to repeat the question, was as you're doing the search, isn't the Doppler going to change, right? There's two things. First, you do it relatively fast, so we're talking like seconds at most for really old receivers. Modern ones, probably milliseconds. But also, even if it's changing, so let's say you're on some vehicle that is accelerating extremely fast, so the Doppler is like ever changing, something like that, you can still, get lucky, like you're searching and this thing is moving, you can still like intersect it. I mean, it might jump over you, right? But if you do a few passes, you're going to catch it, even if it's shifting around if you do it fast. Okay, other questions? No, all right. So, okay, so that's the acquisition step. And what you want to do, you want to acquire multiple satellites, right? So for that, the receiver has, so that basically signal chain that I showed you, imagine that the receiver has multiple of those in parallel, right? So your signal is coming in, and when it comes to Doppler compensation and the correlation, the receiver can have multiple channels. And for each of them is basically acquiring and tracking a specific satellite, right? And again, this is where this idea of code division multiple access really helps, because each of these correlators, if it's correlating with a local replica of a specific code, so let's say this one is doing with course acquisition number 1, this is CA number 2, and so on. And these are known codes. We know exactly what the code every satellite is transmitting is. then if you feed the CA2 into this, you're not going to affect the output of the correlator because the cross correlation of these codes is very low. And that's how kind of like the magic, part of the magic of these codes is that this almost orthogonality through the correlation naturally filters out interferences from other channels, right? So again, in this space of Doppler and pseudo range or tau hat, I'm using time and range interchangeably as you've noticed. So in my mind, like tau hat and pseudo range, which is just tau hat times the speed of light, is the same thing. It's like time and space are kind of interchangeable. But you have this thing which is tau hat between 0 and 1 millisecond and f hat from -10 and 10, and then you acquire a bunch of satellites, and each of them is basically a point in this 2D search map, right? So you acquire your satellites, you acquire at least 4, and then from there on, the job of the receiver is a little easier. So you go into tracking. And as I said, the tracking is basically, on this picture, each of these points over time, it's going to move around because both the Doppler is going to change and the range or pseudo range is going to change. But it doesn't randomize, right? If you do this fast from now to a few milliseconds from now, things don't change that fast. So you only need to like limit, when we started at a cold start, your search space was this entire square, right? Yep.
Are there as many ranging codes as there are satellites?
Say that one more time.
Are there as many unique ranging codes as there are satellites?
Yes, exactly. Yes. The question was, are there as many unique ranging codes as satellites? And yes. There's
Like 30 channels in hardware for every GPS receiver you have?
yeah, you can. But these are the number of channels. I mean, if it's fully implemented in hardware, yes. But these days, these are like software defined, right? So the local replica, there's like, this is all in digital, right? So assume like a microcontroller or an FPGA, and then it can basically in runtime change what code it's correlating against. Old ones, it was all in hardware actually, and yes, they had almost like at the time whatever the number of satellites was. But these days it's software defined, so they have like, I don't know, 8 or 10 channels at a time, and then they kind of flip through the codes and find like which ones give a response basically. Okay, so then the idea of tracking, like when you're cold start, for acquisition phase, you need to search the big search space, which is like 80,000 combinations. But when you go to tracking, you basically just around this, you limit your search by a few bins and see how these things move over time. And that's basically the idea of tracking. So you have like a tracking region around the point corresponding to every satellite. And then you kind of track what it's done. The algorithms for tracking, they can be super, super simple. So for instance, to track tau hat, the simplest one you can do, if we go back to this picture, which was, I believe, here. Yeah, if you go to this picture, to track tau hat, for instance, how it's changing over time, what you can do is that at the output of your correlator, instead of just looking at this peak, if you also look at the sample, like the one before and the one after it, right? And based on like how those two are changing, if the one to your right is increasing and the one to your left is decreasing, that means your tau hat is increasing, right? If the other way around, your tau hat is decreasing. So as easy as that, just by monitoring like 3 samples out of the correlator, you can almost perfectly track tau hat. Same for F. And then you feed these back, so basically, so you can generate this feedback signal. The one for Doppler goes to the numerically controlled oscillator, so the output of that kind of tracks the Doppler shift. And then the one for tau hat goes to your local code replica generator. So that guy also tracks changes in tau. And then almost continuously in time, you can track, sorry, I'm a few slides back. You can track basically all your satellites. Any questions? Okay. So the last thing, which is extremely important that we need to talk about is that, okay, so we kind of have a very good understanding from the physics all the way up to the system level of how the GPS acquires the satellites, finds their positions, finds these time of flights plus the timing offset or the pseudo range to each satellite, but we haven't talked about how do we localize ourselves with all this information. So that's the last piece that we'll talk about. And the idea is pretty simple, actually, once you break it down. So the receiver, so far, what it does is it acquires a bunch of satellites and starts tracking them. And over time, it needs to estimate its own position, PR, using the measured pseudo-ranges to these satellites. And remember that each pseudo-range rho I is the speed of light times the tau hat. So tau hat is that output that you're tracking, which is equal to tau plus your time delay, or your clock delay, which is tau d. So the pseudo-range is equal to the physical range, Ri, to each satellite, plus this error term, which is the speed of light times your timing delay. Okay? And you have these rows for as many satellites as you are tracking, let's say big N, and it's at least 4, right? So these are the measurements that you have. And just to be more concrete, what is Ri? The Ri is the distance from the receiver at point PR to the ith satellite at point PSI. So it's the norm of PR minus PSI, which is the position of the receiver and the satellite, which is equal to the square root of XR minus XSI squared plus Y minus YS squared plus Z minus CS squared. So this is just pure geometry here, okay? Now you have at least 4 of these measurements, and what you're trying to estimate, remember, is 4 parameters. You need, well, your PR, which is an X and a Y and a Z itself, so you have XR, YR, and ZR, 3 numbers, plus tau D that you need to estimate. You can formulate this as a nonlinear system of equations and then solve it using your favorite nonlinear solver. The easiest one is the Gaussian method that we'll talk about. But let's set up the problem first. So basically, you have this function, call it f of, it's a function of the receiver's position and its time delay, or the clock offset tau d, right? And this function, here I'm highly overloading my notation, so be very conscious about what's a vector and what's a scalar. From context, there's no ambiguity, but mind that I'm using like a highly overloaded notation here. So for instance, PR, I'm just going to do it once, and then the rest I'll let you from context. PR is a vector in R3, right? That's our position vector. Tau is a number. That's just a number. So what I mean by this, so f is a function of PR and tau d. So if you stack them together, it's like it takes a vector in R4 as an input. And then the f itself, f of p and tau, it is a vector in Rn. And n is the number of satellites you're tracking, right? So each entry of f sub I, is basically your pseudo-range to the corresponding satellite minus Ri minus C sub tau d, right? So if you have solved your GPS equations correctly, these f sub i's should be almost 0, right? Because we started with the fact that rho I should be actually equal to Ri plus C tau d, right? So with the correct solution, this rho I minus Ri minus C tau d should be almost 0. I mean, there's noise and non-idealities, that's why it's not exactly 0. And that justifies this optimization problem. So if we are minimizing the sum squared of all these terms, which in the ideal case should be all 0, okay? Does the problem setup make sense? Okay, so do we agree that if we minimize this function over p and tau, we have not only localized ourselves, we have also found our timing offset with respect to the GPS system. Okay, let's solve it. So it's a nonlinear function, of course, right? There's like square roots and other stuff. But again, there's many different algorithms for solving nonlinear systems, we'll use the Gauss-Newton. And the way the Gauss-Newton works, just as a reminder, is if our function was linear, so if you had another optimization problem, which was minimize some like ax minus b, norm squared, we all know this is a linear least squares, and we all know how to solve this, right? Like your x hat is equal to A transpose A inverse A transpose B, the famous equation you probably have seen like in 108 or some other course, right? So linear stuff we know, there's closed form solutions. And then nonlinear, the idea of Gauss-Newton is start from some guess for your solution. At each step, linearize this function, so approximate it by some ax minus b, find your linearized solution, use that as your new iterate, and then continue. Linear, so you linearize, solve, linearize, solve, linear solve until you converge. So, and by convergence we mean your solution is not changing much, and that's the point of convergence. Okay, so let's do that. Again, the objective is minimize this function here, and this is the Gauss-Newton. You start from some initial guess of your position and timing offset. Really doesn't matter much, especially at a cold start. You might not have a good guess. Modern receivers do, because there's other ways of kind of guessing where you are. For instance, from Wi-Fi signals these days, you can reasonably well localize yourself. Just from the IP address, you can query on the internet, where am I or whatnot, and that already gives you like a decent estimate of your row. If not, just start random, right? Just pick a point on the surface of the Earth, and then usually these problems are well behaved, and you converge to the right solution. But again, so at each step you linearize your f near the current guess, and then your new guess is the least squares solution using the linearized version of f, and then you update and continue until convergence. And by convergence we mean the value of your f that you're trying to minimize at the current iterate minus its value at the previous iterate. If it's less than some threshold that you can decide, then you call it good and you stop. Okay? All right, so let's go one step deeper and actually derive what the linearization looks like for this. I mean, these days you can just go to Python and just enter this into, I don't know, your favorite, again, like scikit-learn or whatever package you use, and it will take care of it. But I think it's important to not be scared of doing these kinds of derivations. That's why I like to really, from scratch, derive what all the steps are, for instance, for the Gauss-Newton. Okay, so again, the idea is at a step we linearize our function. So, and the linearization is the value is equal to the value of f at the current point, plus, again, don't be scared by the notation. This is just the first order Taylor expansion. This df, which is the derivative, or for the vector case, the Jacobian matrix of f at the current iterate, times the point minus its current estimate. Again, this is, the notation gets a little scary, but this is nothing other than, in the scalar case, if you had some function f of x, you can say my f of x is almost equal to around the point x0. I'm linearizing, so fx0 plus f prime x0 times x minus x0. This is exactly that, except the notation is a little uglier because our x is now this guy, so that's x, right? Or x0, and that's x0. And df is like the f prime for the vector case, and this is x, and that's my current iterate, x0, right? Nothing really beyond that, as simple as that. But let's actually find what the Jacobian or the derivative of our f is. I mean, we explicitly know the function from here, right? These are the fi's. So we can take the derivative of this guy with respect to x, y, z, and tau, and explicitly find the Jacobian. And if you do that, it's actually not too bad. You take the derivative. So for instance, the first row of D is the partial derivative fi, or the first column is the partial derivative fi partial x, and that becomes equal to this guy here, which is the current iterate of x minus the x of the satellite. This is very important, minus x si. So this is receiver, this is for satellite. So xr minus xs over basically pr minus ps, which is the total distance from the receiver to the satellite. Y and Z look very similar, basically. You just, because the function was exactly identical for x, y, z. The one that is different and simpler is tau. Once you take the derivative with respect to tau, you just get minus c, right? And again, if you go back here to where our function was, this is clear. If you take the derivative of this guy with respect to tau, this goes away. There's no tau dependency here. It's just minus c, right? OK. So now you have this. And that's basically your linearization step. So now you can approximate your f as ax minus b. That's a linear approximation. And as I said, explicitly, that's what the a is. That's the Jacobian evaluated at the kth iterate. And the b is this term. And this we know how to solve. Basically, your next iterate is just A transpose A inverse, A transpose B, with the A and B that are coming from the linearization step. So that gives your next iterate, and then you keep continuing until convergence. And again, at the end of this process of Gauss-Newton, you have localized yourself, so you have found your position vector, and you have found your time delay. OK, so how long does it take? After a cold start, usually you don't need that many steps actually for the Gauss-Newton. Usually 5 or so steps is enough to get to convergence, and that's at a cold start, so you almost have no idea where you are. After that, you can always initialize your Gauss-Newton with your previous estimate of tau and p, and then almost in one step always you just converge, which is extremely fast. And that's why the GPS works so fast and reliably, even without much compute resources. OK, one more thing that GPS can do and actually does, which we haven't talked about yet. You could also estimate your velocity in addition to position, which is extremely, extremely useful. And why can we do that? Because remember, we also have the Doppler information. We are tracking the Doppler shift at the receiver. So what is a Doppler shift? Remember, the Doppler shift with respect to the ith satellite is basically given by this expression, which is the inner product of the relative velocity of the receiver to the satellite to the inner product with the unit vector that points from the receiver to the satellite divided by the speed of light times fc, right? So it's the projection of the relative velocity into the radial direction from the receiver to the satellite scaled by the speed of light or divided by the speed of light times the carrier frequency. So specifically, it's equal to your receiver velocity minus the ith satellite velocity inner producted with, this is r hat, which is p receiver minus p satellite divided by the norm of p receiver minus p satellite. So that's the unit vector pointing from the receiver to the satellite over c times fc. Now, if you look at this expression here, everything except VR is known to the receiver, right? You have already solved your GPS equation, so you know your own position. PR is known. PSI is the satellite position, which is known from the ephemeris, right? Denominator, same thing. Speed of light is known. PR, PS are known. FC, that's the carrier frequency, is known, right? The Doppler shift is known. You're estimating and tracking it, so the FDI is also known. And the satellite velocity is also known. Again, because you're very accurately tracking the position of the satellite, you can just estimate its velocity from the consecutive position measurements. So the only thing that is not known to the receiver is this VR, right? So again, you have a system of equations that you can solve and find your velocity. It's even easier than position because this one is linear, right? For position, we had a nonlinear system of equations. Here you have a perfect, it's just inner products and scale factors, basically. So you can form a linear system of equations, solve it, and then you also estimate your velocity, which is, again, extremely, extremely useful. So that's why, if you remember, we said there's some limited odometry that you get from GPS, which is good. Why is it limited? Because remember, the estimate of Doppler is kind of coarse. It's 250 hertz bins. So that's what makes it a little limited, because FD is coarsely estimated. It's not a very, very, very accurate estimate. But other than that, this works perfectly, and pretty much every GPS does that. Any questions about localization and basically the velocity estimation or odometry here? Okay, almost done with the GPS. There's just a final closing remarks I want to make. So one is about the error sources of the GPS. GPS is very error prone, as all of us know from experience. And the main sources of error, one is the satellite position broadcast error. So the ephemeris messages that come, they're not perfect, right? So there could be up to a 1 meter inaccuracy in the broadcasted position of the satellite versus the actual position. So that's one. The other one is atmospheric delay. So there's different layers in the atmosphere, and the two that are troublesome for the GPS are the upper layer, which is the ionosphere, and then one of the lower layers, which is the troposphere. And the speed of light changes in these layers, and it's dependent on the angle of incidence. So that's a source of error, and it can add up to 5 meters of localization error to the GPS. The biggest one is multipath interference. And what multipath is that the signal, what you want really is the signal that is direct line of sight from the transmitter to the receiver, right? And that's, then the time of flight is proportional to the range. But what can happen is that you can bounce off other surfaces. So the GPS signal might hit some other building near you or some other, surface. And some of these surfaces at the gigahertz frequencies, they kind of act like mirrors. So the signal bounces off of that and then reaches you. And then the actual pseudo range that you find is actually then the sum of the two pieces of the multi-bounce. Or it can be more than two, actually. You can have multi-bounce that is, reflected 3 or 4 times. And that completely messes up your localization, because the underlying assumption in the GPS localization is the time of flight is in a direct line of sight. That can introduce up to 100 meters. If you ever use your GPS in downtown San Francisco, it's almost useless. I mean, always I get lost and that's multipath, because you get hundreds of meters of inaccuracy. And the final one is the interferences. There's always like electromagnetic interferences and natural noise in the environment that couples into the signals. Not a big deal, but it can cause up to a meter of inaccuracy. So all in all, you can have up to 100 meters of inaccuracy in the worst case, maybe a little more. But on average, GPS is reasonably accurate, and you get like up to a meter or so. The other one is about time and GPS. So as we saw, a byproduct of solving the GPS equations is you estimate your timing offset, tau d, and then with that, you can compensate that and subtract it from your clock, basically. And then every clock and every receiver is synchronized to the GPS clock. And this is a very accurate synchronization, because even with the slowest code, which is the CA, it's 1 millisecond, 1,000 bins, so 1 bin is a microsecond. So your timing offset is compensated to microsecond accuracy, right? And then it's the amazing, basically, byproduct of the GPS is that now you can globally synchronize clocks across the Earth up to microsecond accuracy. And that's why our timings these days are so accurate. Like back even in like 50s and 40s, time was not this accurate. Like there was, especially globally, the clocks were not synchronized this accurately. That's that. And then the final remark is that GPS is only one implementation of what we call a global navigation satellite system, or GNSS. There's many different versions. China has its own. It's called Baidu. European Union has Galileo. Russia has GLONASS. Japan has its own. India has its own. So there's other systems that do basically navigation and localization using satellite systems. The underlying principle of operation, the math, the physics, system architecture, all is pretty much exact same. And that's why receivers today are called GNSS receivers, the more advanced ones, and they actually acquire signals from different systems and use all of them together to do even more accurate localization. And that's pretty much it. I think with this, we are done with the GPS chapter. And next time, we'll start talking about inertial sensors. Questions? Yes.
For the atmospheric delays, why can't the GPS use a simple atmospheric model?
Great question. So the question is for the atmospheric delays, why can't the receiver use some model to compensate? And the more sophisticated ones do. The way the models work is that the delays are frequency dependent. So if you acquire signals from two separate channels, say L1 and L2 or L1 and L5, you can use that extra piece of information. You know your underlying range is constant, but you get different pseudo ranges because of different amounts of atmospheric delays. And then you mix that with some models that the receivers have based on angle of incidence and thickness of the layers and whatnot. And to some extent, they can compensate. There's more advanced techniques like differential GPS, which also uses ground stations, which don't have the atmospheric delay factored in, and they can even more accurately compensate for it. So you're absolutely right. There's things you can do to, even multipath, there's techniques you can do to some extent compensate for it. Okay? All right, that's it. Thank you, guys.